Okay, we're at 4 minutes past now, so I think I'll get started. There'll be a bit of an introduction anyway, so hopefully more people will join and we can get stuck into the topic today, which is redox flow batteries. And these are an electrochemical technology that have particular applications in grid scale energy storage, which I'm going to talk about today. So I'm going to give a bit of an introduction about myself and then talk about energy storage more broadly and the problems with it, and in fact the opportunities that it represents as well. And we're going to cover a little bit of electrochemistry basics so that we've got a foundation to discuss redox flow battery concepts in more detail. And I'll talk about the variety of different chemistries that can be used in redox flow batteries as well. And hopefully we'll have some time at the end to highlight a bit of the research that goes on at UCL in this area. So yeah, as well as research in redox flow batteries, they also form a part of the course that I teach with Paul Shearing in the 4th year on electrochemical energy and power systems. And so this lecture will give you a bit of a flavor of what you would get in an actual lecture if you were to join UCL, but also, as I say, to highlight a bit of the work that goes on at the sort of PhD and postdoctoral research level within our group. Okay, so yeah, my name is Dr. Rhodri Jervis, or Rod for short. I'm a lecturer here at UCL since 2018, but I actually did my PhD at UCL as well. I did my PhD in fuel cell catalysis. So this is looking at new materials to enable fuel cells to be more efficient and more effective. During that time, we started an outreach program called UCL, which you can see as here in Glastonbury Festival. We went to lots of music festivals and school events and things to teach people about electrochemistry, electrochemical energy storage and conversion devices, which is really quite fun. And I think really interesting as well. UCL is one of the few places where you can actually study electrochemical engineering, which is as part of a chemical engineering degree. And we're really sort of modern facing chemical engineering department with a focus in this area, moving away from more traditional chemical engineering areas such as oil and gas and chemical production, and looking at this really important topic of energy storage and renewable energy as well. So I'll talk a little bit about that today. So I'm part of a wider group called the Electrochemical Innovation Lab. You can see most of us there down in the bottom left. And we're sort of made up of 5 different academics in UCL. It's led by Professors Dan Brett and Paul Shearing. And then along with me, Tom Miller and Alex Retty were hired around the same time as lecturers within this area. And we teach various different types of courses around energy systems and sustainability, electrochemical engineering and power systems, which I share with Paul Shearing. And we also do research methods courses, and Alex has a course on advanced propulsion. I believe Alex's taster lectures on advanced propulsion and Paul Shearing's on batteries, and my previous one on fuel cells are all still available on YouTube. So I'd encourage you to look at the chemical engineering, UCL Chemical Engineering channel on YouTube there to get a bit of a background of some more electrochemical technologies outside of what we're going to talk about today, flow batteries. But as a lab group, as a team, we teach these things. They're all 4th year courses, so master's courses as well. But I think it's a really key area of chemical engineering now. As I say, we're moving into the age of electrochemical power. So moving away from fossil fuels and into these areas. And there's a lot of really interesting challenges that come with electrochemical engineering, which I'll touch on today in terms of flow batteries, but it requires multidisciplinary thinking, people from backgrounds in chemistry, physics, engineering, mechanical engineering, electrical engineering, even some biological aspects to electrochemical energy. So it's a really key area. It's something you can get into from a variety of different routes as well. We have quite a large research group as well in this area, possibly the largest electrochemical engineering research group in Europe. We've got probably more than 70 students and researchers, all looking at various different types of electrochemical technologies. So I'm going to focus today on electrochemical technologies that help with storage, and particularly grid scale storage, so larger storage, as opposed to portable storage that you might have in your mobile phones or your laptops or even electric vehicles at the moment. Obviously, there's been a lot of focus on electric vehicles in recent years, and they're great, but I'll talk a bit about why we need other types of storage and how maybe lithium-ion batteries might not be best suited to that. So the first thing to think about is the actual need for energy storage. As you all know, there's a huge focus on increasing the renewable energy generation around the globe, everywhere really, with fossil fuels hopefully being phased out fairly soon. In 2018, the UK renewables capacity installed was actually surpassed that of fossil fuels for the first time. And other countries such as China and the US are obviously increasing their renewables capacity as well. Most of this renewable energy comes in the form of solar or wind supply. And as you might know, those supplies are actually quite intermittent. So depending on when the wind blows or when the sun is shining, the supply of electricity can be quite variable. And so as we increase the amount or the percentage of renewable sources on the grid, actually this causes quite a bit of an issue. We can't have a fully renewable grid currently because we just won't be able to match the peak demand depending on the supply. So depending on if the wind or sun is blowing. There's a really useful link here where you can see the live status of the grid. And hopefully Mark can put that in the chat for you there. And if you look at the bottom right graph here, this is the status as of about half an hour ago. So we've got a pretty gloomy day today, not generating much solar wind, but you can see we're at about 15% renewable energy supply at the moment. So even though the capacity for renewables on the grid is much larger than that, we don't always get 100% of that capacity being used. And part of that is because of the supply, but also part of it is because of the demand as well. So during the night, for example, we might have a lot of wind supply, but we don't have as big a demand. And so essentially we're wasting a bit of that capacity. And of course, if we try to massively increase the amount of renewables in the grid, then a larger percentage of that capacity might be wasted. And this leads to sort of bad PR about wind farms being turned off and things, and the usual suspects in the media saying that renewables are not a good idea. And so we need to really be able to harness as much of this renewable energy as possible. And without storage, we really aren't able to do that. Storage can help us save money and improve reliability in the grid, and obviously reduce environmental impacts. And it can be a sort of silver bullet for renewable energy. But we need cheap, effective, and long duration storage. Traditionally, storage has been quite expensive and quite difficult to implement. And as I'll show, there's not a huge amount of storage currently. So there's a quote here from an energy report in 2016 that says electricity storage is widely regarded to be the single most important technological breakthrough likely to happen up to 2030, and a game changer in the way that the power system operates. So it's really key. We can see here a map of the UK and the different types of hydro, wind and solar installations. So we're growing these all the time. I'd encourage you to also have a look at the US Department of Energy has an energy storage database, and that shows the number of installed storage facilities across the world, and also the planned ones as well. And that's shown in this graph here up on the top right. And this figure here really outlines how important storage is to a variety of different areas of sectors. Okay, so for electricity utilities providing power to us, of course, this allows them to use more renewables, as I've already said, but also to reduce our dependence on fossil fuel plants that are designed to just turn on for peak demand. This also reduces our expenses, our outlay expenses, but also gives us energy freedom as well. We're not relying on imports of gas from other countries. And that applies to lots of other countries as well. Countries without these natural resources, using renewables and storage can really help them have their own independence in energy. It also helps the grid. The grid is a very complicated and difficult thing to manage, and balancing the supply and demand using storage can be really, really important there, even on very short duration. So we might have a peak demand of a few minutes or just even surges in the grid. And having flexible storage that can respond to that really helps smooth out these demand and supply peaks and troughs. And obviously that can then help with upgrades to the grid as well. But it also has important usage for commercial and residential consumers. So smaller scale storage on the scale of a building, or perhaps a small collection of buildings, or maybe even a village, that can keep things online during power outages. And also help you reduce your own personal utility bills. So there's lots of different areas that energy storage is really helpful. I would also encourage you to have a look at this calculation tool. This is quite a fun way to look at the future energy scenarios for the UK. Of course, there are lots of decisions to be made on these things and lots of arguments about which way is best. particularly around things like nuclear for base loads. But you can, with this tool, you can change the sliders and look at various different mixes of energy demand and supply, and also put storage in, so you have the effect that storage has on the different mix of energy that we use. But all of the future scenarios that are being thought about by government and people in this area include a large increase in energy storage capacity, and also a move towards longer duration storage. So that will be on the order of several hours or perhaps even days, and then maybe even stuff like seasonal storage, where we have, for example, more solar generated in the summer and a lack of solar in the winter. So what does it look like currently? So at the start of last year, the installed operational global energy storage totaled about 185 gigawatts. And there are about 2.5 gigawatts of new planned storage projects currently. But this is predicted to grow quite a lot, and growth by about a third every year, up to a figure of about 1,000 gigawatts by 2040. And you can see that most countries here are planning an increase in storage, particularly driven by China and the United States as well. But currently, pumped hydro storage makes up the majority of that installed storage capacity. And this is simply where we use excess energy to pump water up to a higher point, up to a reservoir. And then when we need that power, we can release the water and generate more electricity. And this is really good. It's really efficient, and it can store large amounts of energy as well. But it's quite limited based on where you can put these hydro plants. And so for this reason, there's a real focus and a real need to look at other types of storage. And in particular, I'm going to talk about electrochemical storage there as a method. Currently, lithium-ion batteries actually make up the majority of new electrochemical storage and new storage projects anyway added to the mix. And this is partly driven by the drastic decrease in cost of lithium-ion batteries recently, and that's been motivated by things like personal electronics and battery electric vehicles. But actually, lithium-ion batteries aren't necessarily particularly well suited to grid-scale storage solutions. So they're very high energy density, which is great when you've got a limited space or limited weight application, like automotive, for example. But they're reasonably resource heavy. They're quite technically difficult to make well, and they also suffer degradation over timescales of sort of a few years. You'll be very well aware, if you keep your mobile phone for longer than a sort of 2-year contract, it starts to degrade in terms of its ability to store charge, and you have to charge it up a lot more frequently. And so that's a bit of an issue. So alternative technologies for grid scale use, where we don't have this restriction on weight or size, energy density of the storage, actually could give us many opportunities to move away from lithium-ion batteries for grid scale storage. As I say, currently the availability and the cost of them means that actually they are having an important role to play in grid scale storage as well. So as I say, there's lots of different types of energy storage, and electrochemical energy storage is just a part of that. As I say, lithium-ion batteries are quite key, but if you look at this maximum cycle lifetime here, you can see that actually there's some problems in terms of their durability. And things like pumped hydro storage have a much larger duration, so they might have a big outlay in cost, but they're expected to last for many more years. I'm going to talk about an electrochemical technology called the flow battery, which actually helps us bridge this gap a little bit in terms of its, or at least its potential lifetime. And so this is a technology that gives us power over the order of sort of hours, maybe half a day, depending on the size of it. And I'll show later that this is very flexible as well. It's quite high efficiency, as are most electrochemical technologies, because we've got a direct generation of electricity from the reactions that are happening in the device. But it's still got some problems, which we'll talk about in a second. This is a picture here of one of the largest pumped hydro power stations in North Wales, called De Norwig. And I should say that this is different to hydroelectricity generation, which might be from a river or waterfall, for example. That's a constant generation from the flow of electricity. A pumped hydro storage system has two reservoirs, one at a high height and one at a low height, and it has a facility to be able to pump that water back uphill, as it were, up to the high reservoir. And so in 2017, the US had majority, 95% storage in the US of pumped hydropower, but this amount of storage was actually very small. So they generated 4 billion megawatt hours of electricity in that year, but only had 4 orders of magnitude less installed electricity storage on the grid at that point. So despite the fact that pumped hydro storage makes up the majority of the installed systems over the last 10 years, actually it's batteries that have been the main focus for energy storage. So I'm going to give a few sort of basic definitions of electrochemistry that are going to be required to understand some of the concepts here in redox flow batteries. You might be familiar with these from school, obviously, but I think it's worth just going over them very briefly. So the first is voltage, which is a sort of potential difference between two half cells in an electrochemical reaction. And 1 volt is what you would get when you carry a current of 1 amp through a 1 ohm resistor, or it corresponds to 1 joule of electrical energy per coulomb of charge. And voltage is what's called an intensive property, and this means that it doesn't matter how big your reaction is, how big your electrode is, you're going to get the same voltage out of it. Conversely, current is what's called an extensive property, so that the current depends on the amount of reaction that is happening in an electrochemical reaction, and therefore if you have a larger electrode, then you're going to have more current. And a current is defined as the rate of flow of charge, and 1 amp of current is 1 coulomb passing every second. I've mentioned electrodes. These are where the redox reactions occur to generate or use this electricity in electrochemical reactions. These are normally good electronic conductors, metals or carbon, for example. And then the final aspect of an electrochemical system is the electrolyte. This electrolyte allows for ionic transport. So this is charged species that aren't electrons, but it's normally a very good insulator in impeding the flow of electricity, but it allows ionic charge to balance the reactions that occur. So we have these reactions happening in a cell such as this one here, and when we're passing electric charge, we need to balance the reactions by the flow of ions within the solution in the electrolyte. And all electrochemical reactions are defined as sort of half cell reactions, but you can't have a half cell in isolation. So you have to always couple it with another half cell reaction to give a sort of full electrochemical cell. And the potential, the voltage of that cell is defined by the difference between the 2 half cell reactions that are occurring on the different electrodes. And these processes can be split into 2 main types of processes called galvanic and electrolytic processes. The galvanic processes are the spontaneous ones. So these are where we have a mixture of 2 electrochemical systems or half cells, and the spontaneous reaction will occur in that direction. So for example, the discharge of a battery or the operation of a fuel cell are examples of galvanic processes. The reverse is true for electrolytic processes. These are ones that are not spontaneous and require an input of electrical power in order to drive them in that direction. And this means that we can use electricity to do useful electrochemical reactions, for example, producing chemicals like hydrogen through water electrolysis, or chlorine, for example, or aluminium. And this means that we can control the direction of the electrochemical reaction by controlling the voltage or the amount of electrical power we're putting into the system. Finally, we need to think about the difference between electrical energy and electrical power. So electrical energy is the energy required to move a charge across a potential difference. You can see here an electron going between 2 plates, negative and positively charged voltage difference. And this is given in units of the joule. And it's simply the charge in coulombs times the potential that charge is moving through in volts. When we're talking about an electron, we have 1 electron volt when 1 electron is passed between a voltage of 1 volt. And we can use this thing called Faraday's constant to give us the amount of charge contained within 1 mole of electrons. Okay. Electrical power is the rate at which that energy change is happening. So this is a rate equation, and this is given by watts, and 1 watt is 1 joule of energy per second. Sometimes you see the units of electricity, the electrical energy, given in terms of kilowatt hours. So this is power times time, and so that is actually a unit of energy. But kilowatt hours are what you will see on your electricity bill. Okay, so 1 unit of electricity in terms of your supplier is a kilowatt hour, and this can also be given by multiplying the current by the voltage that the current is flowing through. Okay. A useful way to think about this in terms of an analogy would be a waterfall, so the flow of water. where in a waterfall, the height of the water is analogous to the potential difference in an electrochemical system, whereas the rate of flow of water is the current. Okay, the rate of flow of charge is current, and so how much water is flowing per second is that analogous amount of current. And then your energy is related to the amount of water you have and at what height it sits. So you can think of it as a sort of potential energy that the system has that it can then give out in a useful form in terms of electricity. And the power is related to the rate at which that energy is dispersed. Okay, so the flow rate and the energy that's contained within the water, i.e., the height and amount of water in the waterfall in this case. Okay. We also need to think a little bit about the difference of electrochemical reactions to sort of normal chemical reactions. So normally in a chemical reaction, all chemistry is about the transfer of electrons, right? So we're in a chemical reaction, we're breaking or forming bonds, and when we're doing that, we're transferring electrons between atoms or between molecules, and that normally happens at that kind of atomic scale. So we're talking, on the angstrom or nanometer sort of scale. And that's great. We can have lots of useful chemical reactions. But when we're doing electrochemical reactions, what we're actually doing is separating that electron transfer away from the sort of intermolecular or interatomic electron transfer and putting the electron into an electrode. Okay? And so when that happens, we can do something useful with that electricity. Or conversely, we can put electricity into the system and therefore drive a reaction in a particular way that we want to. And so the real key difference here with electrochemical reactions is that we're separating this electron charge onto the surface of an electrode. And when we do this, we have two processes, either oxidation or reduction. And oxidation is defined as a loss of electrons, and reduction is defined as a gain of electrons. Okay, so at the electrode surface, we're either giving or taking electrons from our reactants in electrochemical reactions. So electrochemistry is really useful. This separation of electric charge gives us useful electric power, which we'll talk about today in terms of batteries or fuel cells or things like that. As I say, also in electrolytic processes, it means that we can drive reactions to occur that otherwise would be non-spontaneous. And we have this idea of standard reduction potential. So all of these different electrochemical half reactions that you can think of have different potentials depending on the elements used within the half reactions, and these are defined by a series of standard reduction potentials, and you can look these up in tables. And everything is sort of normalized to what we call the hydrogen oxidation or hydrogen evolution reaction, which is just down here. So this is a little bit small, and that's set to 0. And so anything that is above that in terms of its cell voltage will be less likely to happen, as written here, as a reduction, and anything below that will be more likely to happen in an electrochemical cell. And so a classic example of this is the Daniel cell. This is combining zinc and copper and solutions of their ions to give you a spontaneous galvanic discharge of the cell and a voltage which you can calculate from the two different half voltages here of around 1.1 volts. Okay. So how does this fit into what we're talking about today, redox flow batteries? A redox flow battery is a device that allows you to harness this useful electrical power, but also to recharge it and to get to a point where we can store more energy again. And it does this by using two different electrochemical half reactions, as we talked about already. And you can see from this table, there are lots of different potential half reactions that you could use. But essentially, we have two components within a cell whereby these reactions are happening. So we have oxidation and reduction reactions happening during discharge, for example. As I say, these reactions allow you to separate the electron transfer. And so we have some electrodes in the cell as well that will either give us useful electrical power or can take electricity in to do the charging process. But the key thing about redox flow batteries is that we actually store all of these active materials, all of the things that can undergo the redox reactions, in separate tanks external to the cell or the device that does the charging and discharging, which is this box here in the middle. We can store what's called our electrolytes, the solutions that contain these active species, into separate tanks. And this has the really useful a really useful property of being able to decouple energy and power. And so depending on the type of application, you might require high power or high energy storage, depending if you want to store lots of charge over a long time, or whether you need very short amounts of high power electrical charge. And so if you want to increase the power of the redox flow battery, you simply make this cell bigger. Remember that the current depends on the amount of reaction that's happening, and therefore the size of your electrodes to give you more surface for these reactions to happen. And so you make a bigger cell, you make a more powerful device. If you want to store more energy, you can keep your device the same and just simply build a bigger tank and put more electrolyte in, more active materials. So this flexibility in power and energy is really key. And this makes it really useful for grid scale energy storage solutions. We'll talk a little bit about why flow batteries are not particularly useful for portable systems. And that's because their energy density tends to be quite low compared to lithium-ion batteries, for example. But for grid scale storage solutions, this often isn't really a problem. You might couple a flow battery with a wind farm, for example, which is out in the middle of nowhere, and space is not an issue. You can see a couple of examples of actual flow battery installations here, one from Ronke Power in China, which is one of the biggest vanadium flow battery producers in the world, probably the biggest, and a company that's now called Invinity, that used to be called Red T in the UK. And they tend to make these systems in these sort of shipping container units. So these systems contain all of the electrolyte and the cell that does the charging and discharging, and all of the power electronics and other peripheral parts of the system. So that's essentially how a redox flow battery operates. And as I say, we can use lots of different types of redox reactions in these batteries, depending on what voltage you want, or depending on what sort of properties you want from your flow battery. There are lots of considerations that go into the performance of a redox flow battery and how you can get the best possible performance out of them. And a lot of these are engineering considerations. It's how we put these cells together, how we make multiple cells connect in a stack, things like compression, flow, parasitic power loss, all of these things come into it. Things like temperature, the current distribution within the electrodes, all of the sort of inherent thermodynamics and kinetics that are involved in the reactions of the flow batteries, and even just the way we operate these flow batteries. Do we fully discharge them, or do we have partial states of charge, and all of these kind of things. So there's lots of interesting science and engineering that goes into the working of these flow batteries. One particular area that I'm quite interested in is the structure of the electrode material. So I'll come on to that in a little bit. But normally we use a sort of 3D electrode material here to increase surface area. And the properties of that electrode can drastically increase or improve the performance of redox flow batteries. And of course, we can pick lots of different electrolytes and active materials as well. So all of this is governed by the key principles of electrochemical engineering. And this is something that you can learn about if you do your degree at UCL. I want to sort of touch on some of the subtle differences between other electrochemical technologies and redox flow batteries. So two key technologies here are hydrogen fuel cells and a sort of normal battery, like a lithium-ion battery. A fuel cell is a sort of open system whereby, as long as we're supplying fuel, we're generating electricity. So, and that fuel could be something like hydrogen, for example. But they tend to operate just purely in discharge mode, or in constant reaction mode. So we're supplying hydrogen and we're generating electricity constantly. A battery has a defined amount of active material that you can fit within, for example, a cylinder, like these lithium-ion batteries that you can see here. And depending on how much material you have in there will give you a particular capacity. So you can see this battery has a capacity of 3.4 amp hours. Okay, so there's nothing you can do about that. You can't have a higher capacity, and that's called a closed system. With a redox flow battery, you can, of course, increase the size of your tanks and increase that storage. So it's sort of slightly different, but it operates in a similar way as a fuel cell in terms of a flow of reactants into a conversion device, which is the cell. And so it's a sort of halfway between a battery and a fuel cell. You can think of it as a rechargeable fuel cell, perhaps. The fuel cells and batteries have slightly different sort of electrochemistry in the way we think about them. As I say, a fuel cell normally is operating at a particular current. You can change that current, of course, but it operates at a particular current. And depending on how much current you're drawing out of the fuel cell, you're going to get a change in the voltage. Come on to that more in a second. batteries are normally shown, their electrochemistry is shown in a slightly different way, and the voltage of a battery depends on its state of charge. So you'll tend to operate a battery at a particular current density, and this graph shows different current densities and how the voltage changes, but the voltage also changes depending on how much state of charge you have in the battery. So if your battery is 50% discharged, you're going to have a slightly different voltage than if it's fully discharged. And that concept is important in flow batteries as well, because you have a certain amount of electrolyte that contains your charged and discharged species. And so if you're 50% discharged, you're going to have different properties compared to if you're fully charged. But a fuel cell can be thought of as being fully charged the whole time. Okay, so that's why we have these curves of voltage versus current, as opposed to voltage versus the capacity or the state of charge. So we have a kind of hybrid here for the redox flow battery. We have this dependence on the voltage depending on how much current density we're operating the flow battery at, but also depending on the state of charge or the amount of reactant that we have in the conversion cell at any one time. And that can be dependent on the flow rate as well. So flow rate is a consideration that you have to think about in redox flow batteries that you wouldn't in batteries or fuel cells really. You do a little bit in fuel cells. But you can see as you increase the flow rate, obviously you've got more reactants in your cell that are converting. And so you end up with a better performance, i.e. a higher current density for a particular cell voltage. So we need to consider a few more things when we're talking about redox flow batteries. But generally, it's all governed by the fundamental electrochemistry principles, which you will learn about on the course in UCL, and which are really important for all electrochemical technologies. And the first is to think about the cell potential. As I say, a full cell is made up of two half cell reactions. Those half cell reactions will have particular standard voltages, which you can look up in those tables that I showed. And the overall cell voltage is made up of a combination of those two things. We can also use something called the Nernst equation to look at a cell voltage when we have different concentration of reactants in our system. So those tables that I showed earlier are called standard reduction tables, and they're based on standard concentrations and temperatures of the reactants. As we go away from standard conditions, we can look at how the thermodynamics of the system changes and how that relates to a different cell potential using the Nernst equation. So the thermodynamics tell us how much sort of useful energy there is in a system, and that's given by the Gibbs free energy. And that tells us how much useful electrical work we can do by a system, depending on, as I say, the different species and the different concentrations that we have in that system. We also need to think about Faraday's law and electrochemical change. And Faraday's law, he sort of figured out that the amount of current you get out of a reaction, out of an electrochemical reaction, is linked to the mass change or the chemical change in the reaction. So essentially, there's a direct link between how much stuff is reacting and how much electricity you get out of it. Okay, so depending on the reaction stoichiometry, you might be producing 1 mole of electrons for every mole of species that you react, and that 1 mole of electrons has a charge associated with it, electric charge, and that's given by Faraday's constant. So we can figure out, depending on how much solution we have, how much active species we have in our redox flow battery, we can figure out how much potential charge is stored in that battery. So that allows us to size the battery for our application. If we know we need to store 1 megawatt of electricity, then we know exactly how much electrolyte, how much active material we need to put in our redox flow battery. As I say, the key advantage of flow batteries is that it's actually quite easy to do that. We can scale that up very easily by just having a larger tank of electrolyte. And that's more difficult to do with a lithium-ion battery. We also need to think about what happens when we move away from this sort of thermodynamic or equilibrium condition, and what happens when we actually start to draw useful current from our battery or to put current in the battery when we're charging it up. And when we do this, we actually incur losses from that sort of standard cell potential. And this is unfortunate because it reduces the efficiency of the battery, but it's something that we can't get away from. These sort of voltage losses are called overpotentials, and it depends on the current density that we're operating on and lots of other factors such as the type of materials that we're using and the engineering that goes into these cells as well. So we will have some difference in our actual operating cell from what's called our thermodynamic or sort of theoretical operating cell voltage based on these overpotentials. And these overpotentials can be from a variety of different reasons. The first one is what's called an activation overpotential. This comes from the activation energy that needs to be surmounted for an electrochemical reaction to happen. As we draw more current, more of this overpotential is required in order to force the reaction to happen further away from equilibrium. Okay, so if we want to operate at useful current densities, i.e. have a useful amount of power coming out of the battery, then we have to sacrifice some of the cell voltage in order to do that. And by using things like catalysts or changing the temperature of the reactant, we can try and minimize these voltages. But if the reactions are very slow or sluggish, then we actually have quite a significant voltage loss in this case. So we want to try and minimize these activation losses or overpotentials. There are also what's called IR potential losses. So this is just a simple sort of resistance, essentially, in our system. And using the equation V equals IR, we can figure out how much voltage loss we have based on the current density that we're at and the resistance within our system. So obviously there is electronic resistance in the system from the electrodes and all of the circuitry, but also there's quite a significant ionic resistance in the movement of the ions within the electrolyte. And particularly key is the movement of the ions between the separators. So the separator is a material that keeps the positive and the negative electrode apart, and the ions have to travel through that separator. And when they do so, there is a certain resistance associated with that. And actually, these ohmic resistance losses can actually be quite significant in flow batteries, and we want to try and reduce these as best as we can. So having good contact resistance and also having a good ionic transport within our electrolytes. The electrolyte properties are really key there. The final consideration for these losses or overpotentials is mass transport losses, and these are really important in flow batteries. They're important in fuel cells as well, and also in lithium-ion batteries. Essentially, this comes about from the fact that if we try and demand a high current density from our battery, this means that we are, because of Faraday's law, requiring a high rate of reaction. And that rate of reaction can only be satisfied if we can bring enough reactants to the surface of our electrode where these reactions happen, and to have a high enough concentration of reactant species to satisfy that sort of Faradaic link between the current density and the rate of reaction. And this can be really tricky in flow batteries for a variety of different reasons. Firstly, because we have these complicated 3D structures in our electrode through which the electrolyte flows, and also because we have a changing state of charge over the course of, for example, a discharge of the battery. And so as we go to a higher state of discharge, a higher percentage of our reactants have actually already reacted. And so our electrolyte per volume contains a much diminished amount of reaction, so of reactant. And so when we're at lower states of charge, actually demanding these higher current densities is quite tricky. And also, as I said before, this depends on the flow rate as well and the flow properties in RFBs. And the flow rate also incurs a parasitic power loss. So we have to use pumps to flow our electrolyte through the system, and they require a certain amount of power. And obviously, if we have electrodes that have lower resistance to this pumping, have better mass transport properties, then we can reduce that parasitic pumping loss as well. And actually, you'll find in these complicated electrode structures, the distribution of reactants and concentration of reactants is actually very inhomogeneous. So there will be local areas whereby the reactant depletion is very high. This can cause all sorts of degradation issues and performance issues as well. So understanding how these electrodes work and how the mass transport works in flow batteries is really key. And it's a key focus of my research as well at UCL. You can see here some modeling that we've done on these battery electrode structures, and you can see how we can look at the varying concentration of the reactant depending on its location in the electrode. And as you might expect, in areas close to the active parts of the electrodes where the reactions actually happen, you get a depletion in reaction concentration. And this can happen through the thickness of your electrode as well. So you can see here, we've got a high amount of reactant at the start as it's flowing through the electrode, and then that reactant starts to get depleted. And therefore, when it gets depleted, we start to get these mass transport losses becoming quite significant. And so we end up losing voltage for a particular current density. Okay? So these are really key considerations in redox flow batteries that perhaps don't apply so much in fuel cells and lithium-ion batteries as well. But we can try and mitigate this with lots of engineering approaches. This is an exploded view of, actually it's of a fuel cell, but the mechanics of the actual cell in a flow battery are very similar to a fuel cell. And we can do lots of different things such as cooling and reactant distribution, and also stack pressure and stack assembly and things like this that go into the performance of the redox flow battery. So not just the inherent chemistry in the flow battery, but also the engineering aspects that go into building a good battery. And this is quite a difficult thing to do well. Redox flow batteries are quite broad. There are lots of different types of chemistries that you can use. In theory, any electrochemical half reaction you can combine with any other half reaction. In practice, that's not possible, but in theory, you could do that. And broadly, the flow batteries are split into two types of flow battery. A sort of true or classical flow battery where all the reactants and products are in solution. This is something called like the vanadium flow battery, for example, is a good example of this. Or hybrid flow batteries whereby one of the reactants is in a different state, so solid, for example, or even having one of the reactants as a gas, such as zinc air cells, for example. So talked about the all vanadium flow battery briefly there. This is sort of the most widely commercially developed and perhaps one of the oldest examples of the flow battery as well. And this takes advantage of 5 different stable oxidation states of vanadium. So vanadium can exist in the +5, +4, +3, and +2 state, and they actually give quite nice different colors depending on the oxidation state. And so when you're actually operating a flow battery, a vanadium flow battery, you can look at the color change and give some indication of state of charge of the system based on the mixture of these different reactants. And so in the positive electrode, we have, when we're discharging the battery, we're going from vanadium 5 to vanadium 4. And in the negative electrode, when we're discharging it, we're going from vanadium 2 to vanadium 3. So you can think of the charge state as being vanadium 5 and vanadium 2, giving this sort of cell potential of about 1.2 volts. And then we're discharging to vanadium 4 and vanadium 3, which is the sort of lower energy state from which we can then recharge the battery back up to fully charged. So this is often the most widely commercially available, but because of recent increases in vanadium costs, and actually the amount of vanadium that you can dissolve in the electrolyte is not particularly high, people are looking into different chemistries and different systems with increased interest. One of the key benefits of the all vanadium flow battery is that we're using vanadium in both the negative and the positive electrolyte. So that means that although we try and reduce the amount of active species that cross over these into different electrodes or electrolyte chambers, basically, we try and reduce that with an active membrane, there is still some crossover of species that happens. And when that happens, it reduces the capacity of your battery effectively. But in the case of the all vanadium battery, because we have vanadium species on both sides, we can actually recharge the battery in terms of rebalancing that amount of active species in the positive and negative side, because we can just electrochemically oxidize or reduce that vanadium species that shouldn't be there to its proper oxidation state. When we use different materials in the negative and the positive electrode, then that's not possible. We have to do some sort of chemical separation to regenerate the capacity of the battery, and that's quite an issue. One of the issues with vanadium flow batteries is actually the negative electrode. This has a standard cell potential of -0.26 volts. And as I mentioned, that's all set relative to the hydrogen evolution reaction, which is set at 0. So that means if we're negative of that reaction, actually we have a competing reaction of generating hydrogen from water. And so the electrolytes that are used here are water-based. There'll be solutions of acid, of sulfuric acid probably. And so it's possible to generate hydrogen from these electrolytes. And you actually don't want to do that, because that means you're putting some percentage of your useful electricity into a reaction that you don't want to occur. And of course, it reduces the capacity of the battery as well. So this competing negative, fairly negative cell voltage here is a bit of an issue. We can also use different ions, as I say, there's a whole host of different types of ions that you can use, and the iron chromium cell is actually quite a well-developed one. This has a similar sort of cell potential as the all vanadium case, as I say, because you're using different species in the two electrodes here, and so crossover can be an issue. If some chromium goes over to the iron side, for example, then that reduces the useful capacity that you have in your negative side. But the benefits here are low toxicity, it's quite safe, and you've actually got a higher operating temperature than you do in the vanadium battery, because as you go to higher temperatures in vanadium, you start to reduce the solubility of the vanadium species in the electrolyte. Another well-developed chemistry is the zinc-bromine flow battery, and this actually uses the effect of plating and stripping metallic zinc. So you're depositing metallic zinc on the surface of your electrode, and then you're dissolving it when you're doing the opposite reaction. Because of that, actually, it's known as a hybrid redox flow battery, but also crucially, the power and the energy are not fully decoupled in this system, because the amount of zinc that you can plate onto your electrode is dependent on the size of your electrode, the surface area that you have. And there's some other issues with this in terms of the toxicity of bromine and also the miscibility of bromine in aqueous electrolytes. And so you need to add other things into the electrolyte to help that to work. Nonetheless, there are commercially developed systems here. Okay. So I'll just quickly go on to some of the other types of chemistries, but as I say, there's a huge variety of different things. One of the key interests recently is organic molecules, and this is for a number of different reasons. They're very tunable. You can synthesize lots of different types of organic molecules that might have different cell voltages, and also crucially, they might be a bit more bulky. So you can look at some of these metal ligand complexes here, kind of larger molecules. And so this crossover effect through these permeable membranes can actually be reduced with good engineering of these molecules. And there's lots of different types of organic molecules that you can use, and actually quinones are some of the most promising. And there's been some really key research done on this very recently in the last 5 years or so, and looking at quinones. One of the key benefits here actually is that you can have quite a high output cell potential, 3.5 volts. And because the voltage of the cell is related to the energy that you get from each electron transfer, remember that that's dependent on the voltage. And so higher voltage will just automatically give you a higher energy in your system. It does mean though that you have to go to different types of electrolytes. So because water has a breakdown voltage of 1.2 volts, anything above 1.2 volts, you have the potential of splitting water into hydrogen and oxygen, which obviously you don't want to do in these systems. So you then have to use a slightly different electrolyte and solvent, which might be more expensive or might be environmentally friendly, for example. So one of the key aspects of flow batteries, because we have this flow characteristic that we need to think about, and particularly the mass transport of the flow, is actually the type of porous media that we use in the electrodes. So normally flow batteries will use some form of 3D carbon structure, carbon fibrous structure, and these can be in the form of thin papers. And these are just basically taken straight from the fuel cell industry, something called a gas diffusion layer. Or you can use these more sort of thick 3D carbon felts, which are made from weaving a polymer and then carbonizing that polymer to give essentially graphite, so that it's electrically conductive. And those polymers are often PAN, polyacrylonitrile, which is a petrochemical derived polymer. The types of characteristics you want in these electrodes are obviously a high surface area, so you've got lots of sites for reactions. Good electrical conductivity, so you don't have these omit potential losses. Good wettability, so that the electrolyte can surround all of the fibers and therefore give good reaction. And obviously they need to be quite porous and highly permeable, so that we can have as low parasitic pumping loss as possible. Ideally as well, they should be low cost, so that the system costs are low, and they should offer good mechanical and chemical stability as well. And as I say, for the vanadium redox flow battery, they should actually suppress this hydrogen evolution reaction. So that means actually sometimes you're a bit limited in terms of catalysts or metals that you can use in these electrodes, because they might more favorably produce hydrogen instead of do the charging and discharging. One way of also making these 3D carbon structures, and something that we do a lot at UCL, is electrospinning. This is a really cool technique where you use a very high voltage to essentially spin fibers of any polymer into very small nanofibers. And so these are sort of an order of magnitude smaller than the fibers you get in these commercially woven felts, which tend to be around 10 microns in size. These tend to be about a micron or less. So we get these nanofibers, which of course increases the surface area for reaction, which is really great. It also means that by changing the conditions of the electrospinning, we can control things like the porosity, the fiber size, the alignment of the fibers, and the morphology, which all play into the way that redox flow batteries work. So this is really key. Also means you can use alternative polymers, which can give you different surface properties in terms of their chemistry, in terms of their reaction catalyst. And also we can use more sustainable polymers that are derived from biomass, and that's a really key area of some of the work we do in conjunction with Queen Mary University as well. I'll skip over the membrane separators because I'm running a little bit low, but essentially just to say we need a physical barrier there between the electrodes and also between dissimilar electrolytes. So these membranes have to be permeable to the ions that balance the charge, which normally in an acid electrolyte would be protons, but crucially have to try and limit the movement of the other ions in the active species. So in the case of vanadium, for example, we want to stop vanadium passing through. Those are positively charged vanadium ions, but allow positively charged protons to pass through, and that's quite difficult. And so there's lots of work into increasing the functionality of these membranes, but also in using membraneless systems, because sometimes they can be quite expensive as well, these things. As I say, lots of different active species you can use. Essentially, really any sort of redox reactions could be suitable depending on the engineering and the chemistry that goes into it. There's a variety of different options there with different cell voltages for you to have a look at. And also the electrolyte is a key factor as well. So that electrolyte will contain those active species, but also you need to think about things like chemical stability, thermal stability, viscosity, conductivity, abundance, and cost as well. And so you can see an example of some of the electrolyte storage in a large flow battery that's installed in the Fraunhofer Institute in Karlsruhe in Germany. As I say, the key benefit of flow batteries that I want you to take on from today is that we can just build a bigger tank, put more electrolyte in it, and that gives us a higher energy storage without having to go into any sort of complicated adaptations of the actual device, the cell that does the charging and discharging. So lots of types of electrolytes, largely aqueous electrolytes, but there's also non-aqueous electrolytes, particularly for a lot of these organic materials. But sometimes they are flammable or more expensive, but they do allow a larger voltage window to be operated in. Okay, I'll sort of skip through a little bit so we can have some time for questions if we have any at the end. I can see there's one already. But a key aspect that we need to think about is scale up and scale up from a particular cell, from a single cell, which may give us a cell voltage of 1 volt or so in the case of vanadium. If we put lots of these cells together, then we can generate a useful voltage, a much higher voltage in series, and that's called a stack. So we have a stack of cells together that gives us a large scale, grid scale system, redox flow battery system. We don't have to do this, of course, and it's one of the benefits of flow batteries and most electrochemical technologies is they're very scalable. The amount of current that we get, and therefore the amount of energy or power, is directly related to the size of the device, the size of the cell. So how much surface area we have in our electrodes, how many reactions can happen on that surface per second. And so we can scale these depending on the application and depending on what we want to do with them. So in theory, you could use a flow battery to power something small like a phone. The energy density means you probably wouldn't do that, but you can. And you can also then scale them up to the size of these shipping containers and put lots of shipping containers together and provide power for a whole community, for example. But there's a huge amount of engineering that goes into that and into making it efficient and cost effective. There's a big outlay of cost in flow batteries, and that's partly why they're not so commercially developed, or there aren't that many installed across the globe. But I think what sometimes people miss is the fact that that installed cost that goes into that system should last you for many tens of years, when compared to a lithium-ion battery, which may last just 2 to 5 years or something like that. So the outlay cost may be larger, but the levelized cost over the whole operating lifetime can be pretty low. We also need to think about other components in the stack, things like electrical connectors, pumps, power conversion devices, and control and monitoring as well. So scale up, going from laboratory experiments where we do a lot of testing of things like new electrodes and new redox couples, new chemistries, scaling up to a useful size of a flow battery is really difficult, and that relies on lots of key engineering issues. So I'll just quickly go over some advantages and disadvantages. The main one is that we can separate the energy and the power. They're modular devices, and they're also, in theory, very long life. There's minimal degradation. Things like crossover, though, for example, or hydrogen evolution can reduce the effectiveness of the stored electrolytes there. but they're well suited to grid scale storage. They're megawatts systems that have been demonstrated and installed. They've got relatively large, relatively fast response times and startup times as well. Lots of other advantages there in terms of efficiency, and one key one being actually low self-discharge. So if we want to just store that energy over a longer period of time, we can just pump all of the electrolyte out of that conversion device in the middle, and therefore there's no self-discharge that can happen. We have a charged electrolyte in each of those tanks. There are some disadvantages though. We have a lot of system requirements, lots of pumps, flow management, power management systems. They can all cause a parasitic loss in the amount of energy that we have there. And also for the vanadium battery, there's actually a significant cost in the electrolytes, and that's true of a lot of other electrolytes as well. It still needs a lot of research to get to the scale of sort of being widely applied on the grid as well. And they're not portable, which is kind of fine really, because lithium-ion batteries are doing a good job in that respect. So some applications, let's say grid scale storage, power balancing, peak shaving, so taking demand spikes off the grid, backup power, so going off the grid as well. In theory, you could use them in vehicles, and you could charge the vehicles there by replacing a pre-charged electrolyte solution. But because of the volumetric and energy density there, that's not really currently practical with current chemistry, although it could be in the future, depending on if we get some much higher energy density systems. I want to briefly touch on, I know we're at 11 o'clock now, but hopefully you can stick around for a couple more minutes. I want to briefly touch on some of the research that goes on at UCL in this area, because I think it's really exciting. And actually the research gets fed into our teaching as well. So even as an undergraduate, you will learn about the research that goes on at UCL. And there's a huge team of people working on these kind of areas, and lots of people have worked with in the past and continue to work with in this sort of field. And I'd say largely we're looking at new electrodes, new catalysts, and new electrode structures for redox flow batteries. So we use a technique called X-ray computed tomography, and this is an X-ray imaging technique, a bit similar to a CAT scan that you get in a hospital, for example. But we use this to look at the structures of these batteries during operation. So we can look at how well wetted these electrode surfaces are. We can also look at the effect of compression on the flow batteries, and how that affects things like porosity and permeability as well. We've done this with electrospun electrodes as well. So these are much higher surface areas, I mentioned, but with much smaller fibers. And we can look at the effect of things like fiber alignment and again compression on the permeability. A key thing here is actually using modeling to model this permeability. This allows us to do things that we can't actually do with experimental conditions. We can actually look at sort of localized permeability and look at these areas of inhomogeneity within the electrodes, which are really key to how the flow batteries work, and also key to things like degradation as well. So we'll try and optimize this by making better electrodes, and then by imaging them to get the structure of these electrodes, and doing image-based modeling on these structures to figure out which ones are the best in terms of their flow characteristics, in terms of the reactions that are going on in flow batteries. So yeah, as I say, lots of work around permeability and image-based modeling there. We can also look at the advection-diffusion of these, and as I say, this is highly localized and highly inhomogeneous, and so this is something that modeling is really good for. And we're also looking at changing the surface properties of these electrodes using electrospinning to make electrodes from other materials, such as lignin, for example, which is a biomass material. It's actually a byproduct of the paper industry, and so it's very green, as opposed to the petrochemical derived PAN polymers. But also we can tune the surface of these fibers. So even though we're carbonizing these, turning them into graphite, there still remains some surface functionality, some oxygen groups, for example, on the surface, and we can use this to tune the catalyst of the reaction, and therefore minimize these activation losses that I talked about earlier. So we've done a lot of work on this, and we're continuing to work with Queen Mary and Imperial as well on these kind of systems. And this just shows that we can get very different surface properties for these electrospun fibers, but they have very different flow characteristics as well. So we need to think about optimizing both the microstructure and the surface chemistry of these materials. Okay, so I'm just going to wrap up there with some conclusions. So the all vanadium flow battery is still the most extensively researched system, but because of vanadium costs, actually this is changing. Zinc bromine is probably the next most developed technology, but there's a lot of excitement and interest around organic systems at the moment. So this is where a lot of the research is going at the moment, and hopefully that will translate into commercial deployment of these systems as well. Electrochemical engineering concepts are really important in terms of optimizing these redox flow batteries. So we have a set cell potential, a set sort of inherent chemistry depending on what redox reactions we choose in our flow battery. There's a huge amount of engineering and other science and material science that goes into getting the most out of that inherent energy storage capability of those reactions. And so what we need to do is improve the efficiency of these things. We need to reduce the cost of the materials used, the membranes. We need to go into mass production to help bring these costs down as well. Remember, lithium-ion batteries have benefited from 3 or 4 decades of commercialization and really producing these batteries at a very sort of low cost and high rate as well. So flow batteries to compete, we need to start doing that. And we need to look at new advances into new redox couples. And as I say, organic molecules are really good for that because we can tune lots of different properties of them with some clever organic chemistry. I focus a lot on custom-made electrodes, both in terms of improving their microstructure for the flow characteristics, but also in terms of the surface characteristics, the surface chemistry. And as I say, engineering of the whole cell and the materials as well is really important to understand these complex relationships between the performance and the microstructure and the setup of the actual cell. And I'll just finish by saying that UCL is the best place to study electrochemical engineering. So if flow batteries interest you, if some of the other taster lectures on fuel cells and batteries and power systems are of interest, then UCL really is, I'm not just saying this because that's where I work, but UCL really is the best place to study this. So I hope that this has inspired you to go into electrochemical engineering, which is the future, frankly. There'll be lots of jobs available and lots of interesting areas to work in this area. And if you want to do that, then UCL is the best place to come and do that and get your training in this area. So thank you very much for that. Please put any questions in the Q&A box. I can see we've got one already, but we've got a few minutes to do more questions. I'm sorry I've run over slightly, but there's lots of interesting stuff to talk about in flow batteries. So I'll start with the one question we have, and if you want to add a few more in there, then please do. So the question is, do the electrolytes have to be renewed? This is a really good question, actually. So in theory, no. In theory, this is one of the benefits of flow batteries, is that we can continually charge and discharge them, and we've got this tank of electrolyte that's there and available for the whole time. However, as I mentioned in a few of the slides, there are things that can cause the depletion of these electrolytes in terms of the capacity that they hold, in terms of the useful charge that we can put into them. One of those is the crossover. So this is the movement of active species through the membrane separator into the wrong compartment. So if we go back to our view of the vanadium flow battery, for example, or let's take the chromium, the iron chromium one. If we have some species passing over from the chromium side into the iron side, that effectively reduces the amount of chromium that we have in our negative electrolyte. And of course, the amount of reactant is related to the capacity of the battery by Faraday's law. So we immediately then reduce the capacity. That can also cause issues of side reactions and other sort of, deposition, for example, of solid precipitates within the flow battery, and that can cause problems as well. Additionally, we could have these issues of solubility and therefore concentration coming out by changes in temperature as well, and that could cause issues. That could cause deposition of or loss of material as well. So in those cases, eventually we would have to regenerate or replace the electrolyte. One of the key benefits of the vanadium flow battery is that you can do that electrochemically. So you can take if lots of vanadium-2, for example, has passed over into the positive electrode, you can take that positive electrolyte and sort of regenerate it by changing it back to vanadium-2, putting it back into the system and starting with a fully charged electrolyte. This also actually has some benefits. The fact that you can change these electrolytes very easily just by emptying your tank and filling it up with something else. It means that you can kind of very quickly recharge these systems. So you could take the spent electrolyte out, put some new electrolyte in, your system is ready to go and is back online very quickly. And then offline, you can sort of recycle or regenerate that electrolyte. So hopefully you don't have to renew the electrolyte, but you might have to. Other issues might be if you've got some leakage, for example, in your system over the operation of many years, that could be significant. Or if you have these competing side reactions, such as the hydrogen evolution reaction, that obviously depletes the amount of water you have in your electrolyte, and that can then also sort of reduce the solubility of your species in there. Also key there actually is that you're using a fraction of your current that you have in your system, i.e. your capacity, to do a reaction that you're not interested in. And so that means that actually, let's say you've got hydrogen evolution happening on the negative electrode in a vanadium flow battery. If say 10% of your current is being used for that hydrogen evolution reaction, that means you've only managed to discharge your battery to 90%, regardless of what's happening in the positive electrode. So that means then when you charge it up again, you've only got that 90% capacity, and so the capacity will fade over cycles if you have that issue. So that's another problem as well. And so you then need to rebalance the electrolytes. You might not need to replace the whole electrolyte, but you might need to rebalance it every now and again. So those are some of the considerations in terms of the electrolyte renewal. So yeah, as I say, ideally, no, you'd have a closed system that just works for years and years, but there are obviously some considerations and some caveats that go along with that. I should say that compared to a lithium-ion battery, for example, this is way easier to do. So a lithium-ion battery, for a start, is in a sealed cell that you would need to open. But there's all sorts of complicated issues with the electrolytes there, with things called basically the surface that is generated on the negative electrode is very dependent on the electrolyte there. If you try and replace the electrolyte, that can be very tricky. And so you need to really think about new types of cell design for lithium-ion batteries to be able to do that. So that can be quite a bit of an issue in degradation of batteries as well. Okay, hopefully that's covered the electrolytes in a bit of detail there. I've got another question on the miniaturization of redox flow batteries. Is this a feasible project? Yes, is the short answer. So flow batteries and also other electrochemical technologies, as I say, are in theory very scalable. If you think about lithium-ion batteries, actually, we've got very small batteries that are used in sort of implanted medical devices like pacemakers, for example, these tiny button cells that might be less than a centimeter across that provide a small amount of power, but useful power for some device like that, all the way up to powering an SUV vehicle, for example, or in the case of grid scale storage as well, lots of lithium-ion batteries put together can be scaled quite high. There are some issues with scaling to large scale that can be quite tricky, as I've mentioned in the lecture. All sorts of things around flow and around resistance and around stack pressure and all that kind of thing that are difficult. But there are some issues at the smaller end of the scale as well. Mostly what we do in the lab tends to be a single cell and tends to be a relatively small cell. So it'd be something about this big, maybe 5 centimeters squared. And that's just because we don't want to spend an unnecessarily large amount on electrolytes, and also we might be making these bespoke electrodes that, we might be making tens of different electrodes. We don't want to make a huge amount of them and waste a lot of time there. But in theory, they are scalable. As I say, the power that you have in your device is entirely dependent on the size of the cell and the surface area in that cell. And the amount of energy storage is dependent on the size of the tanks of the electrolyte. So if you wanted a low power device that had the ability to discharge for a long time, you'd have a large tank and a small cell. Conversely, if you just wanted very high power but didn't need to store energy, a huge amount of energy, then you could have a very large cell or stack and then have a small electrolyte reservoir. But miniaturization is definitely possible. There are flow considerations when we go into miniaturization. So when we look at the electrospun materials compared to the compared to the commercial materials, you have much smaller fibers, and actually therefore you tend to have lower permeability as well. And that also comes into the case when you miniaturize the other things like the flow fields, for example, the way you distribute the electrolyte across these electrodes. Smaller flow fields will have other flow considerations and pressure drop considerations as well. So miniaturization up to a point is definitely possible. However, the energy density in flow batteries compared to lithium-ion batteries is low. And so for systems where size is a factor, then lithium-ion batteries really are the best technology to go by. And this is why we want to focus on flow batteries for grid scale technology, because they work well at grid scale level. And lithium-ion batteries are really useful for smaller and more portable applications. So we don't want to waste all of the lithium, the cobalt in these batteries, which is a scarce resource. And you know, the technology that goes into these batteries is on a material science level is actually much more complicated than flow batteries. So we don't want to waste all of that in using lithium-ion batteries at grid scale if we can avoid it. Conversely, there's not much drive to use flow batteries at smaller scale because the energy density is not very high. Okay, one more question here. Research studies have showed that indoor air motion, air convection currents in the laboratory have an effect on electrodes. What effect can we observe in vanadium redox flow battery? Can it be a potential research project? Interesting. Okay, so we're talking about the air currents in a lab and how that can have an effect on electrodes. So that would be really key in hybrid systems that use a gas on one of the electrodes. So, for example, a zinc air system. Obviously, the atmospheric conditions there of the lab would be key, but probably more important than the lab air circulation is things like the temperature in the lab. So often these flow batteries would be tested in the lab in a fairly closed system. You would have a tank of electrolyte that actually normally would have a flow of nitrogen over it in a lab setup. In a commercial setup, you tend to just have a sealed system so that you don't have much oxygen in there. And that's because over time, the lower charge of the vanadium-2, for example, can oxidize into higher states of vanadium. That's another way that the capacity can drop in flow batteries as well. So ideally, actually, you want to close your system off from the effects of the lab. But temperature is quite key. So once you get above about 30 or 40 degrees in vanadium flow batteries, you start to lose solubility of vanadium. That can cause deposition in your system. It can clog up the pores of the electrodes, all of these kind of things. So I would say that probably the temperature of the lab is probably more key. Obviously, that affects things like the thermodynamics and the kinetics of the reactions as well that are happening. So maintaining a constant temperature is quite important for the kind of academic research that we do. But I wouldn't say that convection in the lab is that important. What we're talking about more is the convection within the electrodes and the electrolytes, and that is really important. That can have a huge impact on the mass transport in flow batteries. So that is a very, very key focus of what we do for research projects. Yeah, so yeah, normally we tend to try and close these systems off to the lab as much as possible. Yeah, if you see the commercial setups are sort of in these big shipping containers, and all of the pumping systems and all of the pipes and stuff are kind of closed off. There's an example of it. Okay, great. I'll give you 30 seconds or so for anyone to add another question if they want to. But I'll just summarize by saying thank you very much for your attention. I hope to see some of you in UCL in the near future studying these systems. As I say, I think this is the future of chemical engineering, and this is the really interesting stuff in chemical engineering. And don't tell the other people in the department that don't do this stuff, but I think this is the really interesting area of chemical engineering. And it's not just redox flow batteries, as I say, batteries, fuel cells, supercapacitors, all sorts of electrochemical engineering technology that's really key to the future of our grid and the future, frankly, of our planet. So these are enabling technologies that allow the decarbonization of the grid, the automotive sector, the industrial and the domestic sectors as well. These are all going to require electrochemical engineers who understand these systems, right from a basic sort of molecular chemistry point of view, all the way up to the engineering of how we put these systems together in terms of large units on the grid. So huge opportunity here for you to literally change the world with electrochemical engineering. And with that slightly cheesy line, I will say goodbye and thank you very much for your attention.